Now, at some point growing up, most of us have been captivated by one of these, a Slinky. But recently, I found out one of the most mesmerizing things about how it moves is something I'd never seen before, how it falls. So, what's so surprising about a falling Slinky?
That wasn't what I expected.
Well, to help explain is physicist Rod Cross.
The idea is that I hold the top end of the Slinky like this, and then let the bottom end dangle.
So the Slinky's dangling freely.
And then I'm going to drop the Slinky. But I want you to predict what's going to happen. Will the top end fall first? Will the bottom end fall first? Will both ends fall together? Or will the two ends approach each other in the middle?
That is a tough question. When I let go, what does the bottom do?
Shoot up.
It's going to fall. It's gravity.
It's actually going to fall.
Bottom goes up, top goes down.
It might come up together.
You're going to see the top come down to the middle and the bottom come up to the top.
Come to meet it and then drop.
The top will accelerate faster than the bottom.
I reckon that bottom will stay there, this will come down to there, and then they'll both fall.
All right, well, why don't we give it a shot here? I want you to try to watch the whole Slinky as it falls to see what it's doing. It's kind of down, right? 3, 2, 1. The problem is, it's a bit hard to tell with the naked eye just what's happening.
No idea.
I think it came up.
The bottom come up?
I couldn't be sure.
It's all too fast.
Yeah.
To really appreciate the physics involved, you need to see it in slow motion.
Gosh, that's great. That's weird.
That's unbelievable.
It does stay there. Just stays there, like in midair.
It's suspended.
What?
Yeah, it doesn't move at all.
How does that work?
How does that work?
How do you explain that?
Well, you've got to look at what's happening at the bottom end. Gravity's pulling the bottom end down. Tension's pulling the bottom end up. The two forces are equal and opposite, so the bottom end remains at rest. Then I let go at the top end. The tension in the spring changes, but it propagates down the spring, coil by coil, until it reaches the bottom end. And that takes about 1/4 of a second. And then the bottom end falls.
So the tension doesn't actually change at the bottom end until the rest of the Slinky has collapsed.
Correct.
The same principle applies to sporting equipment, like tennis rackets or golf clubs. When contact is made with the ball, a wave travels up the shaft, so the golfer's hands don't feel the hit until after the ball is already on its way to the hole. Now, as a final extension on this experiment, we've tied a tennis ball to the base of the Slinky. We're gonna drop it and see what happens this time. Incredibly, the same thing happens. That's because the Slinky has simply stretched further and reached a new equilibrium where the gravitational force down equals the tension force up. It didn't make a difference.
It is counterintuitive, but that's what makes physics so interesting. That's why I keep doing experiments like this.